Here's a puzzle for you. Take a look at these numbers. Choose a starting point and a stopping point, and sum up everything between those points, including the endpoints themselves. For example, if you chose your start point to be this first item and your stop point to be the fourth item, you would get 3 plus -5 plus 1 plus 3 for a total sum of 2. Can you get a bigger sum than 2? I think you can, it's not too hard. But the real question is, what's the biggest sum you could possibly get? Pause the video and try and answer that if you'd like. I'll give you the answer in 3, 2, 1. The maximum possible sum is going to be 7, which you could get from this range of numbers. This problem is called maximum subarray sum. It's quite a common technical interview question for software engineers, and it's commonly taught in data structures and algorithms courses. Together, we're going to climb through 4 levels of writing code to solve this problem. As we go up in levels, the code gets faster, but also more complex, until we hit the top level, which is an astounding combination of speed and simplicity. Let's start with the most obvious possible approach. We'll look at all the different subarrays we could choose and sum them up. For example, we could have this subarray, or this one, or this one. Maybe our subarray has just one item, but we can't take a subarray that's empty. For each subarray, we walk down it, summing up all the items in that subarray, and then checking if that's the biggest sum we've seen so far. Now you might ask, how many different subarrays do I have to check? And the answer is quite a lot. Let's just think of the subarrays that start with the first item, index 0. We would have all of these subarrays to look at, which doesn't seem so bad, but that's just the ones that start at 0. If we add the ones starting at 1 and 2 and 3 and so on, we'll get all of these subarrays. And for every row of numbers I'm showing here, you would have to walk down that row, summing up as you go. Here's the code if you're curious. Now let me ask you, what is the time complexity of this very rough, simple, brute force algorithm? I'll give you the answer in 3, 2, 1. So there's nothing fancy going on here, just have a look at these 3 for loops. That kind of gives it away that this is going to be a cubic algorithm, O of n cubed. Now, we don't have to look too hard to figure out how to optimize this brute force algorithm and take it from cubic down to quadratic. Here's our array of numbers in which we're trying to find that maximum subarray sum. And here are all the possible ranges that we could sum over that start with 0. I'm showing them now in the order that they would get calculated in as we run through those 3 for loops in the brute force solution. What that algorithm did was basically start at the left for each one of these ranges and sum it up moving from left to right. For example, if we were on this range, that could be our potential maximum subarray sum. We do 3 plus -5 plus 1 plus 3. But at this point, didn't I already calculate what 3 plus -5 plus 1 is? Yeah, I did, on the row right above this, just before now. So wouldn't it be better if I just took whatever the sum was on the previous row and added this last item to that? So that'll save me a lot of time in computing what the sum is for this range. And in fact, I could get that previous row from taking the sum on the row before that and adding the last item of that previous row. And I could do the same thing in a similar way for all the rows above and below this one as well. And now it suddenly looks like I really don't need to loop through all those different ranges that start with 0. I just loop once through this whole range. Here's the code for that. And by the way, if you're studying data structures and algorithms, or even taking a high school computer science course, I'm happy to help you out. I'm a private computer science tutor with a bachelor's degree from UT Austin and a master's degree, both in computer science. I'm also a certified teacher. My link's in the description if you're interested in learning with me. So what'll the time complexity be for this code? I guess it says in the title I probably should have used a different title. This will be quadratic. You can see the 2 for loops there, and that's a huge improvement from cubic. But actually we can go so much faster than that. To find the maximum subarray sum out of an array in less than quadratic time, we can't look at all possible ranges. There's a quadratic number of ranges, so if we check them all, we're just never getting below quadratic time. We've got to take a completely different approach. The problem is just too big to check everything, so maybe the solution is to split it into smaller problems and then have some way of combining the solutions to those smaller problems to get the overall solution. This is the divide and conquer approach. So if we split this problem into left and right subproblems, we know that the maximum possible subarray has to be in one of three places. It's either on the left or on the right, or straddling the boundary between them. Yeah, I haven't really done much straddling recently. Feel like I'm overdue for a good straddle. So basically we just keep dividing until we get down to individual items. Then the max of a subarray consisting of just one item is of course just that item. So these single numbers are all maxes for smaller subproblems consisting of one item. Now divide and conquer sounds like it does two things, divide and conquer, but it actually does three, with the third one being combine, and that's what we need to do now. When the two subproblems we are combining just have one item in each, it's quite easy to understand how we might combine them. The max is either going to be the left item, as you can see with 3 versus -5, or 2 versus -4, or it's the right max, or it's adding two items together, as you can see here with 1 and 3, or 5 and 0. Let's combine again. We'll compare the max on the right with the max on the left, and the max that you could get from straddling the boundary between them. But at this point, it's a little bit less clear how exactly we'd calculate what that straddling sum is. To find the best sum that goes across that middle boundary, we basically start immediately left of the boundary and sum leftward until we hit the left edge, keeping track of whatever max sum we get while summing leftwards. We do the same thing on the right of the boundary, starting immediately right of the boundary and summing rightwards, and keeping track of whatever the max sum we see while summing that right side is. We then add the max that started immediately to the left of the boundary to the max that started immediately right of the boundary to get the max that crosses that boundary. And I'm showing the max that crosses that boundary right below the left max and the right max of each subproblem. We finish combining by taking the max of those three potential choices for the overall max. Let's combine one last time to finish this up. We have to calculate the maximum sum that straddles the boundary between the left and the right subproblems. Here, we get that by computing the sum that ends with this 3 in the middle here, and adding the sum that begins with this 2 on the right side of the boundary. We'd get 7. We take the max of these three choices, and we get 7 for the overall answer. Here's your Python code. Now, this code is significantly more complex than just using a couple of for loops to sum up and compare all the different ranges. But is it faster? Unless you've taken an algorithms course or done a lot of studying on your own, it's probably not obvious that this is faster than just using for loops. So what would the time complexity for this code actually be? Here's a hint. This is quite similar to well-known divide and conquer sorting algorithms that are taught in algorithms classes. I'll give you the answer in 3, 2, 1. So this is time complexity O of n log n. Now this video is not really the place to formally prove that that's the time complexity, so I'll give you the simplest explanation that I can. You can think of these subproblems as kind of being on different levels according to their size. So we have a lot of subproblems of size 2, we have fewer subproblems of size 4, we have even fewer subproblems of size 8, and if this was all part of an even bigger divide and conquer problem, we would have these of size 16 and 32 and so on. They don't have to be powers of 2. And so the basic idea here is that because we have more subproblems of a smaller size on these lower levels, and fewer subproblems but larger size on the higher levels, actually the total cost of combining all these subproblems is going to be the same on each level, and it'll be O of n. How many levels do we have overall? When you see this pattern of repeatedly splitting, that often ends up being a log n. So we have log n levels times O of n work per level to get an overall time complexity of n log n. Now n log n is massively better than quadratic. It lets us solve far larger problems with this algorithm. However, we can still do better, but this code's starting to get complex, and it's really not obvious how to make it better. Sometimes you can take a step back from algorithm design and analysis techniques and just think simply about this particular problem. If you were the computer and you were walking down this array and you can only see a single item at a time, what could you know? If you contemplate that as we walk through a simple example together, you can discover the simplest and fastest algorithm for maximum subarray sum yourself. At first, you only see this one item. Okay, so that's the maximum subarray. Moving on, we see this next item. Now that cannot possibly be the maximum subarray sum. And if I add that to the previous max, I get a max sum that's even worse than what we already had. So there's not much to do here. Moving on. I see a 1. Now this 1 is not the new max, and if I add it to the previous item, still not a new max, and even if I add it to an ongoing sum I had before I hit that -7, that really couldn't be the new max either. However, this 1 could be the start of something that eventually sums to the new max. So I'm going to keep a variable called ongoing sum to track the sum that I have going right now that could eventually become the new max. Next item, I see another 1. Now it's still not a new max, but I add that to the ongoing sum and I move on one more item. Then I see another 1. I add it to the ongoing max. Now the ongoing max is bigger than the previous max, so the ongoing max becomes the new max. Next item, I see a -7, and I add that to the ongoing sum to get -4. Not likely to be useful, and certainly not going to be the max, but let's keep going. I see a 1 next. Now, we could add this to the ongoing sum, getting a -3, but if we only care about finding the maximum possible sum, wouldn't any ongoing sum just be better starting anew from that 1 and not including the negative value preceding it? Yes, it would. So we're just going to set ongoing sum to 1, basically starting a new ongoing sum from that point onwards. Now let me ask, how exactly did I know that I should start a new ongoing sum from that point? I know because 1 is bigger than what I would get from adding 1 to the previous ongoing sum. To be precise, if the current item is bigger than what I would get from taking the current item and adding that to the ongoing sum, then I just set ongoing sum to be that current item, effectively starting a new ongoing sum from that point onward. Here's the last item in the array. It's a 4. Again, if the current item is bigger than the current item plus the ongoing sum, then the ongoing sum becomes the current item. But 4 isn't bigger than 4 plus 1, so 4 plus 1 is the ongoing sum. That becomes the new max sum, and we're done. 5 is the maximum subarray sum here. So what did we really achieve with this analysis? What did we discover by walking through this example? We discovered that it's possible to know the maximum subarray sum without ever looking at every possible range or using any fancy divide and conquer algorithm. We just look at one item at a time. We keep 2 variables and we update those variables in a simple yet subtle way. Here's the code. It's called Kadane's algorithm because it was invented by a man named Kadane. The key points are on lines 4 and 5. On line 4, if the current number is bigger than the current number plus the ongoing sum, then the ongoing sum just becomes the current number. Then on line 5, the max is equal to either the ongoing sum or the old max, whichever's bigger. What's the time complexity here? Yeah, this is just linear. It's O of n. Far better than any of the other approaches, and also much simpler code. Kadane's algorithm is also used as a subroutine in a lot of other coding problems, such as finding the maximum sum rectangle in a 2D array. If you want to practice this problem on Leetcode, this is Leetcode 53. I've got a link in the description. Thanks for watching.